Welcome to the channel. This is the second video in the playlist for pre-calculus review for a calculus course, Calculus 1 typically, though you can use it for the others. Let's cover exponential functions in this video. So first we're going to go over population growth, a very basic example of sort of increasing exponential functions where it's growing. And then decreasing, we call this decay sometimes, elimination of a drug from the body. These are two very standard problems that you learn about. The general form of exponential functions, how we write them and families of them, which we'll get to as well. Other two common examples are half-life and doubling time. We'll talk about this briefly. Some ideas that you want to know for sure. There's the families of exponential functions, kind of taking it from the general form and understanding that. And then exponential functions with base e. These are the most important ones that you're going to be using in calculus and in general. Let's get into it. So one of the first things that we want to look at for exponential functions is population growth. Very common example here. So let's just start with some data. We have some years, 2003, 2004, 2005, and some population in millions, right? So 12,853,000 of some place. Now, the basic idea of the exponential function is just like, so how do we know it's an exponential function? So we know, let's go back to linear functions, and if I say the slope is the same for each 2 points all along the thing, if that number is the same for each set of data points, each pair, then it's a linear function. But if each successive points, the ratio of the population, so we say 13.290 divided by, well, the population in 2003, the year before, this thing, and you do the calculation, you're going to get 1.034. Great. That means that it increased by 3.4%. And the key for exponential functions is that this number, this ratio, is the same through all the data. So 13.747 divided by 13.290, well, that's going to be also 1.34. This will be the same in an exponential function, where we can rewrite this thing as 1 plus 0.034, right? So we have 100% or whatever it was before, plus, well, that 3.4% growth. So the growth rate is 3.4% every year or every successive value. And we can write a function for the population at any given time, t being years since 2003. This is the initial. When t equals 0, the population is that. And then we multiply by this number to the t power. There's your exponent up there telling you, hey, this is an exponential function. The growth rate is 3.4% increase each year. Simple as that. So now let's look at the kind of second most common problem when dealing with exponential functions, and it's the elimination of a drug. And we're dealing with decay here. Before it was growth, and now it's decay. So let's say ibuprofen is eliminated at a rate of 25% per hour from the body. And a typical dose is 400 milligrams. Well, that means that we start with 400 milligrams. I'll use Q to denote our values. And the initial amount here is 400 milligrams. And every hour, there's 25% less of it. So at some time t, the rate of change of the elimination of the drug depends on how much is there. So the less there is, the lower the rate. That's what the key aspect of exponential functions are. It depends on how much is there. And so we can say that in general, Q of t, or the amount at any time t, is Q naught times some rate, or 1 minus the rate, to the t power. Okay, the rate here is 25%, so 1 minus r is 0.75%. And our final kind of answer here is 400 times 0.75 to the t power. And make sure you understand each of these pieces, that it depends on how much is there. That's what the rate of decay is. It depends on how much you have present. And I wanted to say, from the previous one, we had population growth. So some p of t is going to be like that, where Let me draw that a little bit better. It'll be some initial value that we had. And this is growth, so it's concave up. You see the curved nature of this thing where it's kind of like a cup or a bowl. But in decay, it's the opposite. So if I plot Q versus T, well, I'm going to have exponential decay, where it's still concave up, as in it's a bowl or a cup, because see how the curve is pointed upward? This concavity shows up later, and it's important, but it's also decreasing. Notice that the rate of decrease slows down as you get closer and closer to large values of t, where there's not very much of the drug left, so the rate slows down as well. So after considering growth and then decay with the drug, there's two kind of general ways we can write an exponential function, and we'll say that p as a function of t at any time is some initial value times a to the t. So we call this thing the base, and the thing t, the thing up top, the exponent. And this kind of tells us how much it's increasing. For a, in the growth problem, we had 1.034 equal to a, telling us that each year, every time t increases by 1, we have, well, 1 of what we had before, but now an additional 3.4%. every time t increases. That's how it works. And so a quick way to think about this, if a is greater than 1, we have exponential growth or population growth, that example we used before for number 1. And if a is in between 0 and 1, we call it decay, exponential decay. Elimination of a drug, half-life, things like that. It's decreasing. The total amount, which is our function, p, it's decreasing as time increases. So one very important consideration that we want to make when dealing with exponential functions are both half-life and doubling time. So let's just write some definitions. First, a half-life. Well, it's literally how much time it takes for some substance or whatever we're dealing with to have half the amount. How much time it takes. And we'll put that in there, of course. We usually represent that by the variable t, but that's what we're talking about, time. That it takes to have half of what you started with. Okay? The initial amount, we usually call this. And so we can write down a formula for this as well. Do that in blue. So t half-life. Well, you can sort of derive this if you want, but we're just going to write it down. It is the natural log of 2 divided by k, some decay constant. And in general, remember we just talked about this is the general exponential function, but we can also put this k up here to denote how fast it's increasing or decreasing as well. And so we call that the decay constant or the growth constant as well. So there may or may not be a k up there, but you can always read the growth if you have it or not based on what we talked about last time, and sometimes you'll have the k up there, okay? So there's that, and then doubling time, well, it's literally how much does it take, how much time does it take for it to double. If I have some bacteria or some population of rabbits, I want to know how long does it take for it to kind of increase, right? So the half-life, we might use a minus sign up here. I'm up here now at the equation, and you might put a minus sign there next to the k because it's decaying. If it's going to be half of what it was initially, then there must be some sort of decay. So this is how much time, all the same words, but now doubled, okay, not halved. How much time to double. Then in general, your formula, if we rewrite it again, is going to be now k is positive, okay? It'll be a positive value. K will be positive here, but we have the minus sign. So make sure you keep that in mind. These are just some applications of exponential functions, particularly if you take a little bit more math, or definitely in biology, you'll be using this all the time. So the fifth thing in this video that we want to talk about is families of exponential functions. And this is really just a fancy way to say, hey, what does this equation do as I change different values? That is a to the t power. P naught times a to the t. A is the base, t is the exponent. And so if we have larger values of a, or even p naught, what does the graph do? That's all we're really saying. So let's look at t and p. P is a function of t. What does it do as I increase p naught, the initial value? Well, I know that this curve is going to be larger. If that's larger than the red curve like this, then the p naught here is greater than this red p naught. We'll call that p red and p black, the initial values, right? So I know that the initial value of the black is going to be greater than the initial value of the red. And similarly, if I have a rate of steeper increase, let me move this over here so I can do this. And we'll have the same thing. This is t, the independent variable, and p of t on the y-axis. And I say, okay, well, it's going to start at the same place, I think. But now, the blue is going to increase. We're going to have the same initial value, and it's going to increase much faster. Well, a here is bigger than, or smaller for that one. So a1 is less than a2. And a2 being the blue, and that's the base in our general formula here, hey, this is going to increase at a faster rate. All I'm saying is that maybe a1 equals, that's growth, so it's 1.03. And we're just saying that a2 then, looking at the graph, is going to be bigger, so it could be something like this, 1.050, okay? And that's all you really kind of need to know, the general case and what they look like. One last thing here for the families of exponential functions, if I have some decrease, let's say it all starts at the same value. Let me draw a little better than that. Starts at the same value, but we have different rates of decrease, right? Well, we know that, for example, this could be 0.9 to the t in green. This could be 0.7 to the t in black, and 0.3 to the t for the black line. All we're saying is that, hey, they're smaller values, so I know that it's going to decrease at a much quicker rate the closer it is to 0. Because as t gets larger, this thing the rate of change is going to want to get pretty close to 0 here. That's the whole point of these exponential functions. It has to do with the relative rate from the previous data point, essentially. So the last thing we want to talk about is a very special exponential function, and it has the base e. So this is our general function, right? So p as a function of t is some initial value, p naught, times the base to the t power. We can easily write this as p naught e to the kt. So if there's no minus sign, then it's growth. If there's a minus sign, it's decay. So this one corresponds to growth. And this one right here in blue, some p naught e to the minus kt corresponds to decay. So this is what I was talking about earlier with the k values, but now you only use the k when you have a very special base, the number e. The number e is exactly the same as pi. It's a number that goes on forever. It's irrational and just doesn't repeat itself. And you should be very familiar with that one, at least using it on your calculator and writing it out. So we can either write it like this, any exponential function like that, or we can write it like this with the e to the kt. So we're saying that a to the t is equal to either e to the plus or minus k. And that's all we're saying. And this gives us some powerful information when we're talking about essentially a continuous rate of growth. That's what this e means. And the k, we can just pull it out, for example, in our half-life formula and write, the half-life of some substance is natural log of 2 over k, where k is that decay constant that shows up there for the half-life. You may want to remember this one, not necessarily for calculus, but it's a good formula to have. Now, the last thing I want to talk about with this is you definitely need to know what these look like. So just like if a is greater than 1, well, you need to know if this thing is increasing or decreasing. But now we know that if it's e to the positive k, well, it's going to be an exponential growth function like that. And the k tells you how fast it increases, whereas e to the minus kt, well, it looks something like this, basically. Where this is t, this is our p of t. And you want to know what these look like in general, especially for calculus. Being familiar with this function, it shows up all the time, and you're going to want to know exactly what it is. So the last thing we want to talk about is there's a horizontal asymptote always for this general function here, and it's at y equals 0. This is the horizontal asymptote, or HA we say, and then we, a dashed line usually. Talk about end behavior. We'll get into that a little bit more if you don't remember what asymptotes are, but you definitely do need to know and what this looks like. And how there's a shift, then the horizontal asymptote just moves up or down. So for example, if I had e to the kt, then the horizontal asymptote would be y equals 1 for this function here. We're just shifting it up from the parent function, and we're going to talk about that pretty soon here. Translations and shifts, that's the next video or two coming up in this playlist.